All right, good afternoon. Thank you for having me. And I'm here visiting, basically spending my sabbatical leave at Stanford and working with Alison Okumura. I'm so happy to have this chance to participate and share with you my work. I'm going to start with a magic trick. I can read your mind, basically. By showing you this picture, I can tell exactly which motion you're thinking. By showing you this new picture, I can bet my life on the motion you are thinking about is this pouring motion. That was a lame trick, but it is a simple example of this Ideomotor phenomenon people are talking about. So you see, in human brain, we have neurons directly connecting the perception neurons with the motor neurons. Okay, and some of the people call those as mirror neurons. So when you see a cup and a teapot, the pouring motion is triggered, and all of them are actually connected to the consequences, which at this time is the cup become full with water or with coffee. So there's a lot of very useful things we can derive from this phenomenon. For robotics, we describe we want to actually directly connect the perception of the objects with the action. So for example, this one we have the teapot full with water and the cup empty, and we have a pouring motion connecting them, and after that we generate the consequences, which is the cup is full of with the coffee and the teapot is empty. At a higher level, abstract level representation, we can have a set of objects as input, and they are connected with the motion, and have a set of objects as output. So this is usually representing one activity, and we call this representation as functional unit. There are plenty of other examples. So if I have a tomato and a knife, and we can have a chopping motion, we're going to have a chopped tomato and a dirty knife. At a little bit larger scale, if I watch a YouTube cooking instructional video, we can see actually a lot of cooking activities can be represented with those function units. And the good about this is they are actually all connected, and in the end, you are having a graph. For example, at the beginning, you saw the bread and the knife, and basically has the cutting motion. At the end of the video, you see this butter knife with the butter and bread, and you do the butter spreading motion. Basically, this graph has good representation of this video. We processed 65 videos. From each of the videos, we have a graph. We merge those graphs, and we generate this functional object-oriented network. And this network contains about 2,000 nodes, and it's a typical bipartite network. And the red nodes representing motion, and the green nodes representing the objects, and they are all interconnected. And this network have a very good representation of a good amount of cooking knowledge. And I bet this network know better about cooking than I do. So we can do a lot of things using this network. We can obviously use the network to tell us how to cook a meal. For example, if I tell my robot I want to eat barbecue rib for dinner, and the robot can go into the network and look for the barbecue rib node, and then look for available ingredients and also available tools, because the robot just saw them in the kitchen. And then the robot can retrieve this task tree from the network and use the task tree. The robot knows how to make the barbecue rib. However, to physically conduct those motions in the network, in the task tree, we need to have the robot to actually perform those motions. For example, for purring, we have to have the robot know what is purring and how to do those purring. And for our approach, we actually want to mimic human motion, for example, the purring, but we not only want to be able to do exactly that purring, we also need to be able to handle when the cup at a different location, a different material, different kind of water, liquid. And so our approach is to convert this problem into an optimization problem with two goals. One is the generated motion should be similar to the demonstrated motion, and the second goal will be the generated motion should be able to satisfy the new constraints coming with new environment and or new goal and a new start point, for example. Without going into too much of the details, I'm going to just show you some of the results we're getting. We trained a few motions from UT Arlington motion data set, and so our results showing at the bottom corner, and you can see our motion looks more natural, similar to the human, without doing any of the programming, basically. Well, we didn't have much choice. There is only a certain number of motions, so we cannot skip the pulling gun if we want to. All right, so to perform a manipulation task, a lot of times the robot needs to grasp an object. And for example, the purring, the robot needs to be able to grasp the cup and to perform the purring. But we don't want to just generate any grasping we want to, because we don't want to generate the grasp with holding the cup tightly as possible. We want to be able to hold the cup, but also be able to dispense the water. Let's look at another task. So this is a cutting bread, and this is real bread, a real knife. In the lab, we put a tracking system and there track the knife motion, and we also put a force in the handle to measure 6-axis degree of the force and torque. And we can see here the motion is quite simple, but the knife actually needs to provide a substantial amount of force and torque. So the grasping not only needs to provide the motion, it also needs to be able to apply the force needed for the task. So we basically invented two grasp quality measures to help us to define the goals, which basically we want to facilitate the motion, also facilitate the force. So you see, at this time, the robot moving the mouse not only need to do the motion, but also need to providing pressing motion, pressing force, so that the mouse doesn't be lifted up. For the bulb to get into the socket, not only you need to turn the bulb, you also need to be able to press the bulb into the socket. So you want to provide that kind of force. All right. So to summarize, we basically proposed a new knowledge representation that directly links the perceptual representation with motor representation. In the motor representation, you not only need to just consider the motion, you also need to consider the required interactive force and torque so that you'll be able to do the right grasping and perform the work manipulation task correctly. And I want to thank my students for the nice work they have done, and acknowledge the agency, and thank you very much.
The time for welcome question while Karen sets up.